So from Calc 1, we saw that we had, this is my favorite graph from Calc 1, Calc 2. The graph that looks like this. So we've tried to find the area under the curve here from A to B, and what we did was we took a look at the domain, and remember that this is a function from R to R. And we looked at the domain from A to B, and then we cut this up, and the way we did it was nice and even cuts, partitions we call them. And then from here we created the best shape that we knew how to find the area of was the rectangle. And so we created rectangles, and we either used the left endpoint to create our rectangles, or we used the right endpoint. So, or we use the midpoint, and using the left or the right of the midpoint means you're using, for each of these subintervals, what you're doing is you're picking a value, whether it be the left of the endpoint of the interval, the right endpoint of the interval, or the middle of the interval. Sometimes we can even find the minimum or the maximum value within the interval. And then we make a rectangle out of that, and what happens is that we put that into a Riemann sum, and then we get an approximation, and then we let the number of partitions increase to infinity, or we let the length of these partitions go down to 0. Either way, we're talking about the same thing, a whole bunch of these rectangles, and then we get a better approximation until we take the limit, and then we get the exact area under the curve. So that's the idea behind the integrals. Let me run that down again. So approximate, using left, right, midpoint, or anything else within that little subinterval, and then get the height by putting it into the function. And we usually call it xi star, or xi or xi minus 1, depending on what you're looking at. And then the height and base times height. And then the delta x is like the length of the partition. And then we put that, we add them all up. So we have x sub I star times delta x is the area of one rectangle, and then we add up all those rectangles for all the different i's that we have. And then we let the number of rectangles get really, really large. So we take the limit as n approaches infinity, and then that's how we get our integral. The Riemann sum okay. So that's the rundown of what we did back in Calc 1. And what we want to do is we want to do something similar to that. Oops, sorry. What happened? What we want to do is we want to do something similar to that in Calc 3, where we're kind of looking at partitioning some area. So let's take our newest function going from R2 to R. So z is equal to f of xy. You want to think about it that way. Now, like in Calc 1, we had an interval, a simple interval from A to B here to describe something in our domain to be the limits of integration. But now in Calc 2, since our domain is two-dimensional, what we need to do is we need to define, or we need to identify a two-dimensional region. So we need to identify an area. And for us, the easiest type of area to look at is a square. So let's take a look at a square base. To be the area of integration that we have. And maybe your x values go from A to B, and then your y values go from C to D or something. So if I were to look at this straight down on the xy plane, what I'm really looking at is a rectangle. From A to B in the x and C to D in the y. So already our drawing gets a little bit more complicated in a sense that I'm not just looking at the number line. This is like the same story with the limits. In the limits, you go from left to right, you know, limit from the left, limit from the right. There's only two sides to come in. So over here, it's not quite the same, but it's the same idea. It's not just an interval from A to B. It's an actual two-dimensional region. And this is the easiest one right now, and later on we'll talk about trying to find integrals over more complicated regions. So right now this is the region that we're looking at. Sometimes they call this D for domain. Sometimes they call it R for region. So either way you call it, just it's a region. It's a two-dimensional region. So what is somebody supposed to do with this information? Well, if we take the same idea over here where we said it's hard to find the area under the smooth curve like this, so I'm going to make rectangles because I can find areas of rectangles. And then I'll give it specific heights based on some values on my x and y axis. And then my base is going to be whatever, delta x, delta y. So if I want that same idea, an equivalent of a rectangle in 3 dimensions would be like a box, right? So maybe a box, taking a look at a box. Base, which is length times width, and then there's the height. So length, width, and height kind of business. That's easy to find, the volume of. So what we want to do is we want to make a base out of this setup. So what we can do, I'm sorry for moving this D out. I don't know if you could do that easily or you could just erase it. But I'm going to make a partition in here. Somehow partitioning this thing. And if I focus on one particular partition, that could be like a base that I have. Let's see if I can see that partition here on my 3-dimensional picture. Maybe that's where it is. And then I can find the height by picking any point in this rectangular partition that I'm looking at. So maybe I'll pick one, we can pick one right in the middle, we could pick one on the left endpoint, or the lower left corner, lower right corner, the upper left, upper right. I could pick one at the very middle. There's a lot of places to pick a point, right? Just like there's a lot of places to pick a point here. Actually, we only looked at the left or the right or the middle, but technically you can look at anything as long as you're within this interval. Same idea here. You can look at anything as long as you're within this rectangular partition. So the four obvious points are the endpoints, 1, 2, 3, 4, the four vertices of that dot, or that box, or of that rectangle. But you can also choose a middle if you want. And then you can choose a middle of any edge. And so again, there's a lot of different choices. So once you pick whatever you pick, you're going to put that into your function, just like you've put this into the function to get your f of whatever height. You can get the height of that rectangular box region that you're looking for. So we're going to pick a magic point in here. Pick a point. And we'll call it x sub I star, y sub I star, because there's two of them. And then we're going to put that into the function to get our height. Now, the base is dependent on two measures. It depends on an x measurement and the y measurement. So let's take, if we want to take a look at that and blow it up a little bit. So we have the hash marks, and then we have the green mark, and then we have some dots that we may have used. Okay, I don't care about any of that. What I care about, what I care to look at, is the area of this now. This is the length and width times the height business. So if we partition the x with the delta x partition, or size of delta x, and partition the y with the size of delta y, then that's the area of the base that we're looking at. It's going to be delta x times delta y. All right, so we're coming to the same story, right? Except there's a delta x, delta y instead of just one delta x like we did before. Now there's just going to be two of them. And so the volume is going to be given by the base times the height, or the length times width times the height. So that's f of xi star, comma, f of y, or I'm sorry, f of xi star, yi star. That's your height. And then your length and width is delta x and delta y. And that would be the area of this one box. And then we have to add up a whole bunch of them. We're not only adding along with the x, but we're also adding in the y. Oh, I'm sorry. There's a slight change here, change of plans. We're partitioning the x and partitioning the y, and the idea is that those partitions don't necessarily have to be the same, and chances are they are going to be different. So let's call the x partition to be x sub I and the y partition to be y sub j. So j goes from 1 to n, or m, or n, doesn't matter. And then the y partition is our j partition, goes from one to another variable. All right, so this is the definition that's going to lead us to our double integral. So f of xy dx dy, and then your a limits, your x limits go from a to b, and then your y limits go from c to d. So the order of how you place the integrals and the order of how you write your differentials, the dx dy, is going to be important. So dx dy is different from dy dx, because the inner integral here is going to determine the first integral limits, and then the outer integral is going to determine the outer integral limits. Okay, the shorthand notation for double integrals is given by, you see the two integral signs next to each other, but instead of putting the limits, if they want to be kind of vague about the limits for the moment, they just say they want to integrate over a region R or D. I think we call it D. So they put a little sub D below or a little bit to the right subscript of the integral signs. And then they say they want to integrate F, and they can choose to put the X, Y independent variables in there or leave it out. And then instead of dx dy, since it does matter what position you put the x and the y, sometimes they just say dA to say this is a dx and dy combination, and then it'll be up to you how you set up your integral, whether you're going to do dx first or dy first. So this is your shorthand notation for your double integral, and for you to actually compute it, you need to rewrite it somehow into this, and then you'll get your double integral set up. So this information actually falls under the first two sections of your new chapter, chapter 15. So the first part is the theoretical part, and using graphs and numbers to estimate your integral, like we've done in Calc 1, and then we'll actually be computing it in the next section. So we'll try to do both now, and then we'll see how far we can get. All right? All right, so your homework in 15.1 kind of looks like it's set up sometimes numerically, sometimes with functions and stuff like that. But you're asked to make estimates using a particular setup or a particular part of the rectangle to choose, you know, left or right endpoint. But instead of calling left or right endpoint, I tell you there's more to it, so they have more options. So let's take a look at this first problem over here, where we're asked to estimate the volume and let's see how to approach this particular problem. So we have a surface. Z is equal to x times y is our surface. And then we have a region, so they call it R. R, not the real number R, like the ones we use for the set of real numbers, but just a plain type set R that says your x values go from 4 to 10 and your y values go from 6 to 10. Okay? So in a lot of cases, you don't need to see the three-dimensional picture of this, but it's very, very important that you see the two-dimensional domain of this. You have to see what's going on in the domain to figure out your limits. In this particular problem, you want to see your domain to figure out what x star and y star you're going to put into the function. So the first thing I would be interested in doing is trying to figure out what R looks like. So let's draw R. X goes from 4 to 10. 0, 10, 5, 4. And Y goes from 6 to 10. Drawing it here, it doesn't really, not a big deal, but so 4 to 10, 6 to 10, and they're specific about the partitioning. Oh, which one is M? I think M is the X. So the X gets partitioned into 3 equal parts. 1, 2, 3. So let's see how that's going to work out. 4, 6, 8, 10. That looks like it works, yeah? If you really want a mathematical formula for this, it's 10 minus 4 divided by the number of partitions, which is 3. This is going to be your delta x. You know that b minus a divided by n business that we saw back in Calc 1? So this is the mathematical way of finding this. So you got 6 over 3, which is 2. So every 2 spaces over here, your delta x is going to be a measure of 2. So 4 plus 2 is 6, plus 2 is 8, plus 2 is 10. That fits nicely. For your delta x and your delta y, they want only 2 partitions for that. So 6, 8, and 10. So delta y looks like it's going to be 2 also. Okay? So it looks like in this particular problem we're going to be adding up 6 boxes. We're going to find volumes of 6 boxes and add them all up. All right, the first one, well, we're kind of doing the first one already. Use Riemann sum with m is equal to 3 and n is equal to 2, and take sample points to be the upper right corner of each square. So each square, so for this first square, upper right corner, 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 upper right corner. So for the first square, right here, my upper right corner is this point, which is 6, 8. And then depending on which way you go, I'm going to go to the from left to right. 6, 8, and then 8, 8, and then 10, 8. Okay? So these are my points. I'm going to make a list of points here. Your x and your y. xi star, yj star. So 6, 8, 8, 8, 10, 8. And then that's my first row. My second row going up is 6, 10, 8, 10, and 10, 10. All right? So the nice thing is that my delta x and delta y are fixed. So just to look ahead a little bit, the product of my base, or the area of my base, delta x times delta y, is going to be 2 times 2, which is 4. So we'll work that in a little bit later. And we want to plug these numbers into the function f. So my function f of xy is equal to x times y. Now I did this specifically in this way because I'm just going to put f here. I want an f of that function. And all I do is multiply the x and the y. So 6 times 8, ooh, Indra, 6 times 8. 6 times 8. 48. 8 times 8. 4. 10 times 8. 6 times 8. Or 6 times 10. 8 times 10. 10 times 10. Okay, thank you. All right. Okay, so these are my heights of each of these boxes. If I were to collect all these boxes, they'll have these different heights. And then my base is 2 times 2, 2 by 2, so my base is going to be 4. So I can just imagine multiplying each of these by 4. But, you know, when you multiply a whole bunch of them by the same number, 4, and then you add them all up, it's just like adding them all up and then multiplying by 4, right? So what I'm trying to say is that I'm just going to add all these up, and then I'll multiply times delta x and delta y, which is 4. So let's add these up. I got a 12. Okay, I can't add. Is somebody adding for me? $11, $19, $25, $33, $34, $432? I got $342. $432? Yeah? All right. Well, you guys are probably right. And then, so I would multiply this by 4. $17.28. Second? Yep. Okay. So that's it. So I added up all my boxes, and then and I got 1728. So that should be the first answer. So that's the estimated volume of this whole area under the curve, under the surface. Volume under the surface. Let's check. We should check. 1728. All right, so that's good. Now, the next one is looking at midpoint. So it's looking at the same setup, except it's asking you to use the midpoint. So let me do it on the same page here. I'll do it with a different color. Now, it's pretty easy to visualize, right? It's just the middle. But what you have to do is you have to actually look for those values. So I'll have a new set of values. I'll squeeze it in over here. And it looks like my first one is 5, 7, right? You see the middle of that, 5, 7? And then we move on. Looks like it's going to be 7, 7, 9, 7. And then next one up is a y value of 9, 5, 9. 7, 9, and 9, 9. So we'll do the same thing. We'll take each of those values and put it into the function, which is just the multiplying x and y. And then we'll add them up and multiply by 4, which is the base, and then we're all good. So Okay, so just add them all up and multiply times 4, and then that would be your midpoint value. I don't care about the answer. I do care about the conceptual aspect of this. You guys understand what's going on? Or if you don't, can you ask a question? So they used the upper right hand. We could use the lower right hand and see what we'd have gotten. And then the midpoint is generally the best approximations. if your graph is increasing or decreasing, strictly increasing or decreasing. But, you know, we don't know or care at this point how it looks like because we can just calculate it using these values. So I'll put etc. over here. You guys can figure it out. All right, so that's one type of problem where you have a function, you have a partition that they set up using sets, and then you go about it doing it that way. There's some that are more numeric. They give you a numerical table. Remember the wind chill factor table that we saw one time? So they can give you a numeric table and kind of ask you the same questions. And then they can give you a level contour curve picture. So let's see if we could take a look at a couple of those just to start them off, but not actually do them. Here's one with a table. A 20 by 30 swimming pool is filled with water. The depth is measured at 5 feet intervals, starting at one corner of the pool, and the values are recorded in the table. Estimate the volume of water using the midpoint rule with m is equal to 2 and 3. So we kind of got a chart over here. We can kind of look at this as a chart, as our two-dimensional figure, but it might be better if we look at it from our point of view, the way we know how to look. Actually, I don't know. It might be good to look at it this way. Well, let's see. So this is my x set, and this is my y set of values. Maybe it's better to look at it in points, and we'll see if we can do the translation. So it looks like our x goes from 0 to 20. Our y goes from 0 to 30. So this isn't drawn to scale. And then they want our m, our x intervals, our x partitions to go to 2. So that's only cutting this up into 2 pieces, right? So this is 10. And then they want your n partition into 3. So that's also 10. So it looks like our dx and dy is equal to 10, or delta x. And delta y are both equal to 10. Now they want midpoints, so we have to try to identify the midpoints. So the way this is set up, it looks like we're going to get 6 dots again, or six places. So we need to find the middle of each of these things. That's easy enough to figure out, right? 5 and 5 for the first one. The next one is 15 and 5. And then 5 and 15. 15 and 15. 5 and 25. And then 15 and 25 for this last dot. Okay? So finding the midpoint is okay, as long as you got this partitioned nicely and correctly. Now you need to put this into the function, and this is our function table right here, so I have to look at for 5, 5. So when you're doing this, you're kind of using the table as your guide to figure out your input and output values. So your input, you got an input from the x, input for the y, and your output table comes from the body of the table. Your output value comes from the body of the table. So that first one is 4. 15 comma 5, x is 15 down here, comma 5. So that's 3 for the next one. Okay, and you can kind of see, I almost didn't draw this because you can kind of see that from here if you were to draw these boxes because these boxes over here can actually be drawn on these things as well. But either way you look at it. If you can picture that, then that's great. If not, then try to, go ahead and do it this way. Set up our x and y as we know our x and y, x horizontal, y vertical and stuff. And then you can get these values. So the 5, x is 5, y is 15 is 7, and then 15 and 15 is 5. 5 and 25 is 9. 15 and 25 is 7. So these are the values that we would have. You would multiply each of these by 10 times 10, or you can just, and then add them all up, or you can just add them all up and then multiply your result by 100. So the sum of these things times delta x and delta y. And then that's going to be your estimate for this swimming pool. Okay? Is that good? So that's another flavor of Riemann sum, approximating by just using raw data. Okay, I think in your homework I saw one with a level curve. So let me see if there's one with level curves here. Ooh, this one. All right, let's do this one. So the figure shows level curves of functions in the square of 6 by 6. Using the midpoint rule where m is equal to 2 and n is equal to 2 to estimate the following integral. Do we have an integral function here? Oh, I guess we don't have, we're given this. Midpoint. So the midpoint rule, what we want to do is find the midpoint for each of these things. So the grid's already set up for us. So between 0 and 6, 0 and 6, you partition it by 2. So it goes 0, 3, 3 to 6, 0, 3, and 3 to 6. And for each of these, what we have to do is we have to find the midpoint. What color? We should use green. And you can see that the midpoints here are just going to have to be approximated. All right, so we have these points. This would be about 1.5, 1.5. Let's call it 3/2. That's 1.5, right? That's 1 point. Here's another point. That's 3, 4, 4.5, 1.5. What's 4.5? 6/2, 9, 7/2, 9/2. And then 3/2, 9/2, 9/2, 9/2. Okay. So this is really going to have to be an approximation, because this is all we got here. We got f. We want to put this into the function, and I'll draw this squiggly to say it's not exact, and I have to approximate. So 3/2 and 3/2, it goes from a level of 3 to a level of 4. So what would be a good guess for this? 3.4. I was going to say 3.5, but it looks like it's a little closer to 3. Just by a tad bit, 3.4 would work. I'd probably say okay to 3.5 also. Does that first one look okay? Let's make this a dot shape. The next one, let's make this a square shape. And what level is this, approximately? Between 5 and 6. So this dot is between the 5 level and 6 level, so 5.5 looks pretty good. All right, this one, let's make this into a triangle. So this dot over here is going to have a height of what? 5.25. I was going to go 5.4, but whatever. And then the last one, let's make this into a different shape, like a star. .5 between 7 and 8 levels. Okay, so you see how we use the level curve to get those values? What's our delta x and delta y equal to? So the m and n were equal to 2. That's the number of partitions, but remember that the delta x is the distance or the length of these things. Generally, it doesn't have to be all equal to each other, but it just makes it easier for us to make those computations if they are all equal. So nice even partitions. Along the x, there's a length of 3. Along the y, there's a length of 3. So I think that's it. We add these up, multiply by 9, and we should get our estimate. Why don't you guys add this up, because I'm curious to see what their answer is. What is it? Let's take that and multiply that by 9. What is it? Let's try that. They didn't ask us to round off for anything here, did they? Enter a number. What was it again? Oh. You can improve the estimate by increasing m and use a larger number of subrectangles. Larger number of smaller subrectangles. That's confusing. All right, I just care about the number. Let's see if we get the number correct. They should be really flexible because it's like really estimating. Oh, they took it. I wonder how much give they have here. Maybe we can put anything here and it'll be correct.
Maybe after we got it right once, they don't change it.
Oh. Okay, so this is wrong. So there's some error that they're accounting for here. But I think if you get close enough, then they'll be good. All right. I think those are the types of problems that you should be expecting for these things. Now this is a nicer picture than what I had. They actually are drawing the boxes under as the drawings are being shown over here. So if you work through, I realized that the labs weren't due yet. They're due on Tuesday, right? Yeah, they really should have been done before class today. So how many people did the labs already? Okay, handful. Okay, so. Because we had that break and I didn't make the announcement that the lab should be due before then, I just said, okay, I'll just make it due on Tuesday. So if you start working on the lab, you'll see this a little bit clearer. I think this is a good problem to look at, and I think this is one of the lab problems, yeah? Okay. All right. Beyond this, though, we don't want to, of course, compute things by hand like this unless we're if we're really stuck with a level curve and that's all we have, or we're stuck with a table and that's all we have, then we really have no choice aside from estimating this. But most of the time we're going to be given a function, and so we're going to use analytical techniques. So that's what we're going to do, is we're going to use analytical techniques. So I just want to start you off with these integrals as iterated integrals. And this is going to be a lot more powerful than just plugging in numbers into, plugging points into your function and then getting the height and then, multiplying and getting estimates. Here, we're going to begin to get exact values, taking advantage of the Riemann sum idea. So our task is to get our region figured out So I think I'm going to use R now, since they used R. Our task is to get our region figured out and then take advantage of the functional methodologies that we've been using before. You know how when we started talking about partial derivatives, we fixed a particular value and then we took the derivative assuming that that was constant. So we're going to do the same thing. Let's see. Let's fix the y first. Does it matter which one? Okay, so what we're going to do is we're going to fix a y value first. Yeah, let's fix a y value first. So let's call this y star to say that it's fixed. So our function that starts off as f of xy, our function goes from R2 to R. We'll have a fixed y to begin with. So when you fix the y, then you have f of x y star, and y star is fixed now, so it's a constant. So what we can do is we can integrate f of x y star with respect to x. Since x is still our variable, we can integrate this. And let's say we're going to integrate this from a to b. What are we going to get when we integrate that? We're going to get an area under the curve, right? So what curve are we looking at? Well, first of all, the curve that we're looking at is some curve up here. On my surface. So what I've actually found here is the area of one slice So this is your x value, your x-axis, your z-axis, and then I found this area of, I found the area of this one slice of my region. Can you picture that? So imagine now what we have here is a function. When you do this integral, you're setting y star fixed. So then your result is now going to have something, a function of y star in it. Because when you integrate with respect to x, the x variable disappears. So you know that term dummy variable? It doesn't matter what that variable is, because if you have a definite integral from something to something, that variable that you're integrating with respect to is going to go away, because in the end, after you find the antiderivative, you're going to plug in these limits. And so that's called a dummy variable. So what happens now when you do this integral is that you're going to get a dummy variable. X is going to disappear, and now you're just going to get a function of y star, which we are holding constant, but it's still going to be a value. Now, what happens if I choose a different y star? Let's call it y circle star. Uh-oh, what's a circle star? That's like bad, isn't it? Okay, let's draw an upside down star. Okay. So my question to you is that, what if I had just another random y variable here, y variable value? Let's say it's an actual value that we picked up. And I put it into this g function that we got from integrating with respect to x. What do you think I'm going to get? What? No, not yet. I'm just putting this one value of y there. Geometrically, what am I going to get? Same thing, but how? So what same thing? What same thing? The same curve. Well, not just the curve, but an actual area. So I would get a different area, but from a different slice. Right? I would get that different slice. So what I'm trying to get at is that this g function is now an area function where I have areas of a bunch of these slices. Now what I could do is I could take that g function and integrate that g function with respect to y along the y, let's say going from C to D. And let the y vary. And so I would be, remember the integral is just a really fancy way of adding up a whole bunch of an infinite number of little things. So I'm adding up an infinite number of these slices, the area slices. Think of it as bread, sliced bread. This is the best thing since sliced bread, right? You take a slice, you get one area. You take another slice, you get another area. If you put all those slices together, you get the whole loaf volume. Right? That's exactly what we're doing here. Okay? So what did we do first? Let's see if we can summarize what we did. First, we took the integral of f of xy with respect to x from a to b, right? Then we took the integral of whatever result that we got there. We called that result g, but without calling it g, let's just leave it as an integral here. Then we took the integral with respect to y from C to D. So first, with respect to WRT, with respect to x, then with respect to y. So if we do it that way, we're going iterated integral from inside from the inside integral to the outside integral we could take these integrals one by one and from inside to outside build our function, and that's called your iterated integral. So if we think about the iterated integral as just sliced bread like this, we're going to integrate with respect to one variable first, the other one's fixed. We're taking area slices. And then we're going to add up all those slices together, put them all together to get our whole volume. Then that's your iterated integral. Okay? Next time we're going to start off with an example where we're actually going to do computation using our techniques of integration from Calc 2. And then that would be more analytic than what we've been doing. Questions? All right. Have fun with your labs.